Okay. So the first, this work, we will have the final difference like this part, and this work function is write down as this function. So if we use the index notation, similar, if we want to take the x direction, we should take I equivalent to the 1. Then we should get the same result like this minus partial x partial omega x, like this, and the area, the area times the dx, so then we have a dv like this part. So this should be the x direction of the work rate. So if we want to take the y direction, this I will become to the 2, and the I will become to the 3 for the z direction. Okay. So that's summation for all the direction. Then this work basically is the external force due to the pressure, and also due to the shear stress. So if we rewrite this work rate, you can use the vector identity to rewrite like the right hand side. So the right hand side we write down like this because the first term, this diverge of stress, then we relate to the momentum equation like this. So from the momentum equation, we can relate the gravitational force and the surface force with the particle acceleration. So basically, we want to see the gradient of stress. Use this relationship to get the stress related to the acceleration and the gravitational force. And these two terms is the same like previously we write down the total energy that have potential energy and the kinematic energy. This is related to the kinematic energy, and this we relate to the potential energy. So that means in the total energy, the equation 2.34, the 3 terms, there are 3 terms, potential energy and kinematic energy. can be cancelled out by this term and this term. Okay? So in the work, we will cancel out these two terms. Okay? Okay, so if we get rid of this potential energy and kinematic energy, we will have our internal energy related to the heat flux, just like we use this, and we cancel out these two terms. Then your internal energy, we have a heat flow, like a dt dq. Then we substitute this term to here. And also the work, because of the work, we have these two terms. Then this term is cancelled out, so we only left this term. Okay, so this term we contribution to the external force like the stress. So the first, this cancel out part is the Bernoulli equation part, because in this the kinematic energy and the potential energy, we consider the right hand side and the left hand side, both they have this term. Then right now we like to know how the contribution for the heat and the stress contribution to the internal energy. In very special case, if there is no temperature difference, so there is no temperature difference, internal energy, should they change or not? If you don't have a flow field, doesn't have a temperature difference, so that means they don't have a heat flow. So this term should become to 0. And as long as this term become to 0, that means your internal energy doesn't change. But in this case, because your stress, your viscosity with contribution, something like viscosity. So this viscosity with contribution, something like a friction. This friction, we become to the useless mechanical energy. So that's why the Bernoulli equation, they reduce their useful energy later on in the downstream. But the energy cannot disappear. So this energy will become to the internal energy. That will become to the thermal energy. So the thermal energy cannot completely convert back to the mechanical energy. Okay? So last, we can see there are some contribution for this kind of stress. Basically, is viscosity stress that will contribution to this kind of internal energy. That means your system will increase the temperature. Then this increased temperature because viscosity or because of friction, and this reduced energy make the Bernoulli equation reduce their mechanical energy. Okay, so here we can see their contribution is come from the normal stress and also the shear stress. And the shear stress, mainly we will talk about the dynamic viscosity. This part, their contribution is not so significant. Okay, so from this internal energy equation, if we first to divide this stress, we divide this stress into the shear stress or viscosity stress, and this viscosity stress defines like this one, like equation 2.27. In the Navier-Stokes equation, we are talking about stress mentioned like this, and we can divide the shear viscosity stress like this part, and the normal stress like this part. So the normal stress contribution, basically we can rewrite this normal stress contribution because your flow field, basically we are regarded as the open system that flow in a different location that maybe have a different kind of pressure. So this pressure, basically we can use the mass conservation equation to rewrite this term like right hand side. Okay, so in the right hand side, if we substitute this part into this energy equation with the internal energy, then we can summation this internal energy and the pressure and the density. This will become to a new physical parameter, enthalpy. Okay. In this textbook, they use maybe the E, P, low, but in some of the thermodynamics book, for example, in this university, we are use the internal energy like the U, pressure, still P. Your density is a specific value. Okay, so your definition of enthalpy is like this, but they can rewrite like this way. So the left-hand side, we become to the enthalpy. The right-hand side, if we still keep this temperature gradient and the viscosity contribution, then and the pressure change with a different location. But this term basically is like the friction term we are just mentioned. So this term, their contribution is always should be the negative to the total energy. Okay, so if you are use the Bernoulli equation, this will become to the minus term. But if you are using the thermal energy, this will be always a positive, because your flow with a friction, then without any heat flow, they cannot reduce the temperature. Your flow, if you flow very fast, they will increasing the temperature because of friction, because the fluid inside they have some kind of friction, and this friction will reduce this mechanical energy to become thermal energy. So for this part, because we are talking about internal energy, or we're talking about the entropy, then this term is always positive, because this friction with contribution to the increase the thermal energy. So you can substitute this shear stress, this term, and with velocity gradient into this term, because there is a very complicated term. So I just make it that easier. You can refer the textbook, okay? And from this equation, you can see there are many terms is a square. So the square doesn't mean they must be positive. So then if you want to make this become to the positive, they must have some kind of a condition. For example, like the coefficient must be positive. Otherwise, if every term is a square, then you cannot be negative. Okay? You want to get a positive value. So the other thing is these two terms, if they want to compare, then how to compare to each other. So because they are this relationship, so they will give this bulk viscosity, bulk viscosity and the dynamic viscosity have this relationship. So usually we will, last time we mentioned that we equivalent to the 0 because this term, when this term will become to the minima term, they equivalent to 0, then this mu will equivalent to the 2 over this kind of relationship. But they should satisfy this equation, then they can make this become to the positive. Okay? So here we are looking about the thermal energy view. If we have this kind of relationship, then your energy term, how to contribution to the internal energy or enthalpy. Okay, so energy equation, there is another view. It's from the binary equation. So the binary equation, from the point of view of a binary equation, we become to the mechanical energy plus thermal energy. We become to the total energy. And the mechanical energy, that's kind of potential energy and the potential energy and the kinematic energy. We just neglect in our calculation in the internal energy. Because of internal energy, this term, we are get rid of potential energy and the kinematic energy. Because they are conserved, because the stress can change this, they are conserved. But this term is not conserved. They will change the total energy, then convert the useful energy into the thermal energy. So if you use the binary equation in the halos, doesn't mean their energy disappear, just mean the water increase the temperature. Okay, but if you do the calculation, this kind of mechanical energy compared to the thermal energy, usually is very minor. Okay, it's not so significant because your friction, usually your friction with the velocity, you can do some quick calculation. If your friction with the velocity like 3 meters per second compared to the water, this maybe is not enough. Then if they reduce to 0, you can calculate how much kinematic energy loss. And this loss energy maybe just increase the temperature, maybe like 0.5 degrees C or maybe 1 degree C. So compare really heating, this kind of mechanical energy, order usually is 1 order less than the thermal energy. Because the thermal energy, usually we use combustion or we use different kind of temperature difference. Usually that's thermal energy, we are considered 10 degrees C or 100 degrees C. That kind of order compared to the mechanical energy is quite significant. They are quite different order. Okay, so you can consider mechanical energy is just like the human being, or just like some kind of animal. They are doing the work. This kind of energy level is like the mechanical energy. Then we maybe pour some heavy material, heavy stuff, okay? But the thermal energy level is like the machine doing. So after the industry revolution, we are usually provide a heat to the machine. So the machine need a lot of energy. Usually it's like this kind of a different level. Okay. So right now, look like we have a new generation coming. It's the AI. I don't know. This kind of thinking process and the thinking speed, how fast they will change. Okay. So let's maybe introduce another revolution. Okay, so this basically is the energy equation we are talking about. And there are some kind of simplified case for the energy equation. For example, like incompressible flow. Then if we consider this energy equation, we can simplify this energy equation, but maybe we just have 1 minute left. But I will do a quick summarize, because Gaussian equation so far we already introduced to you already. So include the mass conservation equation, then momentum equation. We are talking about the stress and the external force. Right now, combine them, you can see the energy equation. Then they will use maybe both of mass conservation equation result and the momentum equation result. So usually, we will use the 3 equations coupled together to solve the problem we have. Okay, so supposedly we should use this Gaussian equation to solve some particle problem. Usually the particle problem is like the Cauchy flow or Poissonian flow, or like the different kind of boundary condition. And I believe some of you already talked about the Cauchy flow is a flat flow, and the Poissonian flow is like a pipe flow. But we probably have only 3 more lectures. Yeah, we have 3 more lectures left. Okay, so yeah, I don't know. I don't know how much we can talk. Okay, basically just like the schedule. Usually we like to talk about Stokes problem, because the Stokes close this momentum equation. They have a Stokes first problem, Stokes second problem. Usually, it's very classical problem. We better to look at, but yeah, because the timing, we try to get as much as I can. Okay, so yeah, so that's pretty much about the basic equation. Because after basic equation, we will talk about some kind of particle problem. Then maybe I will neglect some part, for example, dimensionless and the control variant, because the control variant supposedly every undergraduate student should know, but usually we will review that very quick, like the control variant and the dimensional analysis. Then, anyway, let's see. Okay, I try, because the control variant is important to relate to the basic equation as well. In the control variant also have a system and have a space. Similar like a differential equation that consider the one particle and one location. So that is a differential and integral. They are relationship. Then because many fluid mechanics equations very complicated, you cannot solve. So that's why we use the dimensional analysis. Okay, but that part we can go faster. Maybe later on we talk about some particle problem that will